Today there is no doubt that the entire intergalactic space is filled with plasma. The images taken by modern telescopes show this in an impressive way. The way plasma glows depends on the density and degree of its heating or electrification. The glow modes can be divided into 3 categories. When plasma is relatively cool or just slightly electrified, it is transparent like a normal gas. The interstellar medium and the solar wind are examples of transparent plasma. At higher temperatures, plasma begins to glow. We use this for fluorescent tubes or plasma screens. For example, the sun's photosphere and the northern lights are glowing plasmas. It should be noted that the density of the plasma is rather important. At low density, even a relatively low temperature is sufficient to make plasma glow. Dense and hot plasmas begin to glow very strongly. Arc discharges, similar to those caused by lightning, are the result. An electrified plasma behaves very differently from the gases and liquids we come into contact with in everyday life. When a current flows in a plasma, a magnetic field is inevitably created at a 90-degree angle to the direction of flow of the current. The resulting magnetic field compresses and structures the plasma. This is called the pinch effect. Current-conducting plasma thus organizes itself. It primarily forms filaments. With modern astronomical methods, we find just such filamentary structures wherever we look. Neutral gases in a vacuum do not behave in this way and never form such structures. Here we see current-carrying plasma under the influence of the pinch effect. The northern lights also offer beautiful examples of electrically conductive plasma filaments. When such filaments are aligned with the flow of an external magnetic field, they are called Birkeland currents. At the beginning of the 20th century, the Norwegian physicist Christian Birkeland was the first to systematically study the aurora borealis, attributing its filamentary structure to electric currents in the ionosphere. In his famous Turilla experiments, he even succeeded in recreating similar luminous phenomena in the laboratory. If you take a closer look at electrical discharges, for example in a commercial plasma sphere, you can see that large filaments are actually made up of several small ones that are wrapped around each other, but do not fuse completely with each other. If we look at the movement of electrons in a filament, we can see the reason why. In an external magnetic field, the electrons perform spiral movements. The parallel component of their motion causes 2 filaments to attract each other over greater distances. But the circular component of their movement has an opposite, repulsive effect, which becomes more pronounced at shorter distances. Filaments initially attract each other at greater distances, but repel each other more and more as they get closer and finally reach a state of equilibrium. We end up with 2 filaments wound around each other. This interaction mechanism is of paramount importance on a cosmic scale, as widely distributed plasma can be concentrated very efficiently in this way. There are many observational examples of the winding helical shape of Birkeland currents. Knowledge of the pinch effect can help us better understand the evolution from quasars to galaxies, which was presented in the previous chapter. We know from experiments that concentrated electrical discharges, for example in a plasma focus, can create a kind of ball lightning. Such ball lightning is called a plasmoid. It now makes perfect sense to think of quasars as cosmic plasmoids that are produced in the center of a galaxy, as in a plasma focus. Experiments have shown that the magnetic field that holds the plasmoid together begins to collapse over time. As a result, two jets of matter shoot out of the plasmoid along the axis of rotation. On a cosmic scale, this phase, in which the quasar becomes unstable, could represent the transition to very active X-ray and radio galaxies. Here we see the famous radio galaxy Cygnus A. The small dot in the center is the galactic nucleus. Two jets shoot out and form huge clouds of plasma where the magnetic field weakens. With the creation of these clouds, the next phase in the life of a galaxy commences. As early as the mid-1980s, the American plasma physicist Anthony Parrott simulated the formation of galaxies from two plasma clouds of this kind. Let's take a look at the simulated formation of a spiral galaxy from the electromagnetic interaction of these plasma clouds. After the former quasar has almost completely collapsed in the middle, the two plasma clouds begin to drift towards each other due to the pinch effect, that is the mutual attraction of their magnetic fields. The movement of the plasma in the weak primary magnetic field of the collapsed quasar causes the positive ions and negative electrons of the plasma to be driven in opposite directions. The ions are much more massive than the electrons, which causes the clouds to start rolling like billiard balls. The center of the electron stream in the two clouds shifts, and so do the secondary magnetic fields, which ultimately leads to the rotation of the clouds around each other. Even at this early stage, the two plasma clouds show extremely complex motions that are actually observed. Gravitational models, on the other hand, have grave difficulties in accounting for these motions. In them, the two gas clouds, which are thought to be electrically neutral, simply drift towards each other and may even begin to orbit each other. But their intrinsic motions are inexplicable. And so they are simply converted into a starting parameter and programmed into the simulation. Since the electromagnetic forces inside the plasma clouds are stronger than those outside, the clouds are stretched, forming the typical spiral arms. Due to the increasing repulsion with increasing approach, the plasma clouds do not penetrate each other, but remain separated from each other to a certain extent. A kind of magnetic cushion forms in the center, which may later serve as a new plasma focus to create additional quasars. The overall magnetic attraction thus holds the new spiral galaxy together as a whole, but at the same time a repulsive short-range force prevents the two initial plasma clouds from completely merging. The result is a plasma galaxy that has exactly the same complex rotational properties as those observed in real galaxies. Here, the interplay of plasma clouds can be understood using the example of the structure of Birkeland currents. The evolution of plasma clouds is analogous to that of current-carrying filaments. The fact that these are realistic computer simulations and therefore accurate, albeit simplified, representations of natural phenomena can be seen in the plasma experiments of the American physicist Winston Bostick, who shot just such plasma clouds at each other in a magnetic field in his laboratory, observing the typical spiral structures of galaxies. In the previous chapter, it was suggested that the yellowish galaxies in Stephan's quintet once emerged as quasars from the blue galaxy. It also appears that two of the quasars have come closer to each other due to the long-range magnetic attraction and are in the process of forming a spiral galaxy. Anthony Parrott used only Maxwell's equations of electromagnetism in his computer simulations. Gravity was completely ignored. It is not surprising that gravity had no role to play. the electromagnetic forces are at least 10 to the power of 36 times stronger than gravity. This is the reason why gravity can be easily overcome even with small magnets, although the entire mass of the Earth counteracts it. As soon as electromagnetic forces come into play, the weakest of all forces, gravity, is no longer relevant. In addition to the complex rotational properties, the observed magnetic fields of galaxies could also be recreated in Parrott's simulations. Here we see the development of the magnetic fields of two plasma filaments depicted schematically. Parrott's simulated plasma galaxies showed the same characteristics as real observed magnetic fields down to the last detail. In addition to the rotational properties and magnetic fields, the model of electric galaxies solves another problem of gravitational-dominated Big Bang cosmology. In the 1960s, the orbital velocities of stars and galaxies were measured. As is the case with the planets of the solar system, the stars of galaxies were expected to decrease their velocity with increasing distance from the center. But that's not the case. Rather, they remain constant beyond a certain distance, which is in direct contradiction to Newton's and Einstein's laws of gravitation. In order to somehow explain away this observation, which put gravitational cosmology in dire straits at the time, dark matter was invented. If only enough mass were distributed around a galaxy, the observed velocities of the stars would eventually be achieved. Of course, the invention of dark matter brought with it further problems, so that dark energy had to be invented to compensate for the effect of dark matter on larger scales. In the end, Big Bang cosmologists ended up with their standard model, which contains only 4% real, observed matter. All this only because electromagnetism had not been taken into account, and thus the extremely weak gravity had to be made stronger at all costs. As radio astronomy reveals, the plasma of a galaxy reaches much farther than the visible stars. This plasma forms a conductive medium that rotates in a magnetic field. The whole thing works analogously to a unipolar motor or generator, as first developed by Michael Faraday. This well-known electrical phenomenon provides further insights into the nature of galaxies. Analogous to the unipolar generator, enormous electric currents are generated in the galactic plasma, which flow along the spiral arms into the center. The resulting secondary magnetic fields further compress the plasma through the pinch effect, ultimately creating stars. We will discuss this in more detail in the next chapter. The electric currents converging in the galactic center, in the area of the magnetic cushion, create plasmoids, which once again give rise to filamentary, helix-shaped jets during their collapse. Modern astronomy provides impressive observations of such jets. Recently, such electric jets have also been detected in our own galaxy. Cosmologists were perplexed as to the origin of the electrons. However, these electric currents are anything but mysterious once the electrical nature of galaxies has been recognized. Another example is provided by ESA, which presents this illustration of huge, winding plasma jets on its website. However, the word plasma is conspicuously absent, because as always, great efforts are being made to avoid this taboo word of gravitational cosmology. Instead, we are led to think of molecular gas. The electrons shot out of the center during the collapse of one or more plasmoids then flow back along the galactic magnetic field into the spiral arms, where they close the circuit. And now we go back to the problematic orbital velocities of the stars. The magnetic fields of the arms act like rigid spirals that move the entire plasma uniformly. Electromagnetism prevails here, which is incomparably stronger than gravity and can easily hold the plasma of a galaxy, including its stars, together and move it as a compact unit. So the rotation of galaxies might not adhere to Newton's and Einstein's gravitational equations for one simple reason: because gravity plays virtually no role on the galactic scale. Black holes were once introduced into cosmology to explain the seemingly gigantic energy output of quasars, which may simply be due to a miscalculation of distance. And these fictitious black holes were later used again when extremely dynamic processes were discovered at the centers of galaxies. But again, the all-electric cosmology has no use for these irrational monsters. The electric currents forming the spiral arms converge in the center, where they heat up the plasma to extreme temperatures. Additionally, large magnetic forces are at play. It goes without saying that we might expect tremendously dynamic processes in such an electromagnetic stress region. Supermassive black holes are completely superfluous. Galaxies are definitely not collections of neutral gases. Therefore, they are probably not held together by the hopelessly weak gravity, which, on top of that, has to be artificially strengthened by invented dark matter. Rather, plasma galaxies could be electrodes in a gigantic cosmic discharge process. The filamentary structure of the visible galaxy clusters, which is a real observation, directly indicates such an electrical process. Before we take a closer look at the electromagnetic nature of stars, there is one more observation on the galactic scale that needs to be explained. In addition to redshift, the cosmic background radiation is considered to be the second pillar of Big Bang cosmology. In our electrical model, this radiation is not an echo of a Big Bang at all, but a direct consequence of the ubiquitous cosmic plasma,